Okay, so here in a Wheatstone bridge, when we adjust these resistors, there might be a situation where there is no current through this galvanometer. When there is no current through this galvanometer, the potentials at these 2 points have to be same. Then only there won't be a current flow. So A, B, C, and D, we can tell that at balance condition, VB is equal to VD. If VB is equal to VD, then drop AB and drop AD are equal, right? Drop AB is equal to drop AD. Now, let's say the current through this is I1. Then the current through this also has to be I1 because there is no current flow through this. If this is I2, then the current flow through this is also I2. So we can write that VAB is equal I1 R1, I1 R1, and VAD, that is equal I2 R2. So that's first equation. Similarly, we can tell that VBC is equal to VDC. So BC is I1 into R2 and VDC is I2 into R4. So that is the second equation. Just divide the first by the second. If you divide 1 by 2, you have R1 over R2 is equal, this is R3, right? This is R3. That is equal to R3 over R4. So, can you remember when we discuss resistors, when we discuss finding the equivalent of resistors, they are also be dealt with something similar. When the resistors are in a ratio, then there was no current through the resistor that was at the center. Then it is the same idea over here. But what's special here? Here we are adjusting 3 of the resistors, keeping one of them constant. Okay, is the idea clear of a Wheatstone bridge? So note 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 number 1. out of 4 resistors out of 4 resistors, if 3 of them are known, if 3 of them are known, 4th could be determined. 4th could be determined. Note number 2, to increase the accuracy, to increase the accuracy of the circuit, to increase the accuracy of the circuit, all resistors are in same order, or approximately equal. So what do you understand by in same order? For example, when we have all the 2 resistors, we have 2 resistors in 10 ohm and the third resistor is 10,000 ohm, then they are not in the same order. In this case, getting the balance condition is really hard. and it may not be accurate. Okay, so that is the idea. Note number 3, when a battery is replaced, when a battery is replaced by another, the balance condition, the balance condition is unaffected, is unaffected. So even if you replace this battery with another battery, when this is in balance condition, it will remain in balance condition. So you know the reason, right? When they are in ratio, this resistor won't work. So it is the same principle. Okay, completed the know. Instead of having the galvanometer only, we have another setup. We have a galvanometer, and in series to the galvanometer, we have a high resistance, and then we have a key to short circuit this high resistance. So this is also a key, okay? So why do we need this? Galvanometer is protected by higher resistance, by higher resistance HR from large current. Okay, is the idea clear? So here we are, when we adjust now, as it is mentioned, we have an unknown resistor. We are going to adjust all the other resistors. When we adjust the resistor, unless it is the balance condition, there will be a current through this. There will be a current through the galvanometer. We know that galvanometer measures a small current. So if the current is huge, it might damage this galvanometer. So what we do is, first we keep the switch open. And we have a higher resistance in series to the galvanometer. So obviously the current is low. So we adjust these resistors. Until until the galvanometer reading becomes 0. So that is a rough balance. Now you close it. Now you close the key. Again, this galvanometer will slightly deflect because small current will start to flow. Once again, you make minor adjustments, not coarse adjustment, minor adjustments to these resistance and make it 0. Okay, so that's note number 5. When galvanometer is connected in series with high resistance in series uh, connected with high resistance in series approximate balance length. Approximate balance length. No, approximate balance is obtained. Next, the high resistance is short circuit by closing the key. By closing the key. And then next the HR is closed, is short circuit by closing the key, and then accurate balance is obtained. Then an accurate balance is obtained. Now, when we are going to start the experiment, we have to make sure the circuit is working. For that, we can try this. Keeping three of the resistors fixed and varying the resistance of the fourth resistor from 0 to infinity. So 0 to maximum, okay? 0 to infinity. Then the galvanometer deflection. Then the galvanometer, it is a center zero galvanometer, okay? Then the center zero galvanometer has to deflect, center zero galvanometer has to deflect from one side to the other side through the center zero, through the center zero. Okay, is that idea clear? To ensure balance condition. Noted up to this, and I will clear with this last statement. Sarah and Shahama. Note number 7. when battery when battery and galvanometer are interchanged at balance condition at balance condition, the balance is unaffected. The balance is unaffected. Okay. So just look, these two circuits are actually the same. Just imagine this battery coming between these two, and this is going out there. Both the circuits are similar, right? So it's not going to make a change. You can make uh, you can make Wheatstone bridge using a ammeter also. We have resistors R1, R2, and R3, and we have a switch at the center. Okay. Now a ammeter is connected to the battery. Ammeter is connected to the battery. This is switch S. When S is open or closed, if reading of ammeter, if reading of ammeter remains same or remains unchanged, then the balance condition is present. Then it is in balance condition. It it is in balance condition. You will note it. And write down applications applications of Wheatstone bridge. Number one, meter bridge. Second, potentiometer. Okay, so yeah, once you completed, me know. Applications of Wheatstone bridge, meter bridge, and potentiometer. So next topic, meter bridge. One minute. Meter bridge. Meter bridge, we use the same concept of Wheatstone bridge. So here, we have 1 meter long wire. To this 1 meter long wire, we connect a very thick strip of conductor. Thick strip of conductor. Here also we have a thick strip of conductor, and at this edge we have another thick strip of conductor. And here we connect two resistors that we want to compare. R1, R2. And here, in between, over here, we connect a galvanometer. To this galvanometer, again, we have a high resistance and a switch to protect it. High resistance and a switch. And here we have a sliding key. Okay, we have a sliding key. This is a galvanometer, center zero galvanometer, and a sliding key. And here, now we have a cell. We have a cell. Now, do you understand that this is similar to the Wheatstone bridge? Look, here you have two resistors. Here we have wire. So this wire is also a resistor. So this will have some resistance R3 and R4. So when we move this key, when we slide this key, at some situation, these ratios will satisfy. R1 over R2 will satisfy R3 over R4, right? Then we can measure this length. We know that resistance is proportional to length. So instead of R3 over R4, we can write L over 100 minus L. So we can compare the resistance. Okay, so if if one of the resistance is known, let's say R2 is known, then we can determine what is R1. So is the idea of the meter bridge clear? It is similar to the Wheatstone bridge. So if you got the idea how a meter bridge works, then that's it. It's easy from there. Yeah. So draw the circuit. The meter bridge. The meter bridge is based on the Wheatstone bridge. Wire, the 1 meter wire used is made of is made of nichrome or manganese because because their their resistance is greatly unaffected unaffected by temperature. So we know when current starts to flow in a wire, it will get heated up. If it gets heated up, then its resistance will change. But in case of nichrome or manganese, those are alloys, their resistance are much unaffected by the temperature. Okay, so that is why we use those wires. The ends of the wires, the ends of the wires are are inserted into thick strips as shown. When the circuit when the circuit is completed, the sliding key or jockey or contact key is moved along the bridge wire until balance condition until balance condition is obtained. Okay. So let's say this is point P, where the balance condition takes place. Point P is called the balance point. Balance point. And length L, length L, always measured, always measured from positive terminal, always measured from positive end, is called is called the balance length. Okay, when the bridge is at balance, when the bridge is at balance, let's say this is point A, this is A, B, and B at balance, we can tell that R1 over R2, R1 over R2 is equal RAP over RPB. But R1 over R2 is equal, instead of this, we can write rho L over A, and here we can write rho 100 minus L over A. Simplifying, we have R1 over R2 is equal L over 100 minus L. Okay, noted after this. When you are page through book, you must be able to try the question on the Wheatstone bridge. Okay. We have some notes to write on the meter bridge. We will note them down in the next session. Up to now, you must be able to try the questions from the Wheatstone bridge in your page through book. So before the next class, try them. And if you have any questions that you could not get an answer, make sure you ask them, okay? So have you noted? Saja, have you completed noting? Okay, so I'll end the session. Assalamu alaikum.